From Austin, Texas, is Cerfe Labs.
All right, last but not least, I'm Greg Yarrick. I'm the CTO and a co-founder of Cerfe Labs. Also here today is Eric, our CEO. We'd like to thank iTech for giving us the opportunity to discuss CeRAM, a dual-use microelectronic memory based on a new class of materials. In the microelectronics field, alarm bells are ringing. The big three memory technologies, flash, SRAM, and DRAM, are all stalling. And this lack of ability to keep up with Moore's law is leading to these kind of terrifying headlines you see from industry pundits. In the future, the microelectronics roadmaps are really dependent on us finding memory that's better than what we have now. Memory is already over half the system cost, half of the speed bottleneck, and half of the energy problem in current microelectronic systems. And this extends from energy-constrained IoT devices all the way up to high-powered data centers. And furthermore, advances in AI are dramatically outpacing Moore's law. So it's predicted to deploy future AI, it's going to require memory that's about 10,000 times more energy efficient than what we have today. So while the memory market is an enormous $200 billion and demand's insatiable, down in the technology trenches, there's a lot of uncertainty about the future. Of course, that means a lot of opportunity. We saw this at ARM Research. We noticed that virtually all of our architecture roadmaps were limited by the memory they could access. Eric was the head of ARM Research. I was the technology fellow. Lou was the senior device physicist. And the collection of properties that we want out of a memory are fairly straightforward, but taken together, they're fairly elusive to attain. Flash, the most recently developed memory technology, is slow, power hungry. Slow, power hungry, and it stopped scaling years ago, but it's the best non-volatile memory we have. It's also not reliable. So case in point is Tesla, who could put a car into space, but their choice of flash in their controllers led to a fleet recall. So at ARM Research, it was our job to find emerging technologies that would help drive these roadmaps forward, no pun intended. And after a significant amount of due diligence, we concluded that the various emerging memory technologies, none of them would meet the general purpose needs required. But we came across this one technology. It was an early TRL, but it showed a unique ability to check all the boxes required by a good general purpose memory. The inventor had previously invented and successfully commercialized ferroelectric memory, which has shipped billions of units. So we decided to incubate this technology and help advance its TRL. This is where it gets interesting for NASA. So due to a unique physics of operation, it also supports extreme harsh environment requirements for future NASA missions. For instance, we've shown operation below space cryogenic temperatures up through temperatures above the commercial semiconductor market. And this memory retains information at temperatures that perhaps only NASA would care about. By the way, all these are just tester limits. We really don't know the range. We have work going on to expand our understanding. So a true harsh environment microelectronic memory would reduce the SWaP-C of most space-based systems. And at NASA, you need the full gamut. You need hot, cold, radiation, EMS. We think we have this technology. I mentioned expanded understanding. We have a DOE SIBR to look at the cryogenic side. This is in the QIS area. And we have an AFWERX SIBR to look at the hot side. In addition, we've initially shown CeRAM to be unphased up to a megarad of gamma radiation, and we have more extensive radiation testing as part of this AFRL SIBR. So let's look at this from a national missions need. What you would like to do is deploy adaptable autonomous intelligence in long lifetime systems, and you have a small number of systems. This set of requirements is best met by an FPGA. You need a harsh environment FPGA. That technology does not exist. Furthermore, you need this to be non-volatile memory, because you deploy systems in what's called normally off computing, a phrase NASA takes to the extreme. The DoD is trying to spur development in this missing technology, but you can see they're aiming for criteria that don't meet your needs. You need expanded temperature range, and to deploy sophisticated AI and imaging, you're going to need gigabits and not megabits. All right, wait a second, Greg. You said SBR, and ARM is not a small business. Well, we kept hitting research milestones at ARM, to the point we licensed the technology fully. And then at one point, it required a business unit level decision at ARM. And at the end of the day, this business didn't fit ARM in 2020. So in October of 2020, we spun out. Rather than sticking around ARM and looking for another research project, we felt strongly enough about this technology that we took the 87 patent families, the research programs at Symmetrix and iMech. iMech's the leading site for commercial R&D, and off we went about a year ago. In addition to the 3 people you already met, we spun out the head of operations for ARM research and 3 people hired along the way for their test, design, and device physics expertise in memory. We also have a world-class set of advisors and consultants. Jason, the CSO of ARM, is on our board. Depesh and Rob provide seasoned technical advice. Dave has deep experience in commercial memory markets. Jason similarly on the US government microelectronic side, and Sam helps us with our IP strategy. Our mission is to use our R&D expertise and advance the TRL of this technology to the point where it can be adapted by commercial sites. Now, we've watched other companies fail while spending over $100 million building out labs, design teams, et cetera. We're opting for a different path. We're going to partner our way to commercial success. This is very much in the line of our business model. We think we have advantages that will help us on this type of path. First, we have fundamental new materials innovations. We have the fundamental patents. Unlike most of the other technologies, this is not leaked around the globe. In hindsight, it was nice to build a good IP portfolio before launch at a company that understands how to make good IP, all except for the maintenance costs. And second, and why we're excited to talk to iTech, is this technology addresses unmet needs at NASA, DoD, and other US government interests. And these lower volume, lower density needs provide perfect stepping stones towards the really strict requirements to deliver to the commercial market. Here's an example from one of your suppliers. Ozark IC is a leading supplier of extreme high temperature microelectronics. And they've told us they could use even 128 bits above 150 degrees C. In the RF space, which is a focus of our AFRL SIBR, system providers in that area tell us there's a market for 100,000 devices, discrete micron-sized devices per year in that field with the characteristics we have in our devices. And thirdly, seasoned team, the majority with previous startup experience, an extensive set of commercial connections, and the DNA to stay small and partner without building all the infrastructure ourselves. Do we think we're going to take over a $300 billion market in 5 years? No. But with the size of semiconductors and memory in general, even niche markets are gigantic in this area. So even though none of those emerging memory technologies is that astounding, that particular market's expected to grow to $44 billion in 10 years. Another big point is for a lot of startups, the problem's the business model. But in our case, memory IP, licensing royalties is a well-established business model. So we're a little over 1 year old. We're well along the way on phase 1 of our business plan with the 5 SIBRs, the research program at iMech. But as far as complete core research, I want to talk a little bit about exactly what. So the actual device is quite simple. You just deposit an oxide on a wafer with top and bottom electrodes. This is a very common construct in CMOS fabs, the metal insulator, metal capacitor, except in our case, carbon doping turns it into a magic switch. Carbon doping of oxides is the invention. We have that patent. It's also not a one-time magic thing. We've got a universal characteristic that we've shown in multiple materials, multiple deposition techniques, multiple electrodes. This amount of flexibility is very important for reducing risk to end commercial manufacturers. And we'd like to thank DARPA for funding a lot of the work in this part of our program. Technology possesses a lot of traits that have limited other emerging memory technologies, has a very large on-off ratio, operates at very low voltage. And our program at iMech has delivered significant TRL advancements as well. We've shown that this can be integrated below state-of-the-art dimensions, that it's a very fast switch, that it can integrate on arrays on 300 millimeter wafers, and that it retains its special temperature advantages at the nanoscale. So it's this collection of properties that really gives us excitement about this memory as a future candidate. I'd like to talk a little bit about the dimensions and put them in perspective. Remember those headlines before? That was due to lackluster SRAM scaling, which has not been scaling according to Moore's law, and that's projected to continue. If it does, it will continue to eat up more and more of the chip area. This will become more and more painful. So there's a great deal of interest in finding something that can replace SRAM and get us back on the Moore's Law bandwagon. I'd like to point out, so the dimensions we have proven at IMEC would make a memory more dense than 3 nanometer commercial SRAM. So I want to look at this from a fab perspective. TSMC makes about $4 billion a quarter, $4.5 billion a quarter on 7 nanometer wafers. So a very modest shrinking of the cache size, resulting in a 15% die area savings, would result in about $700 million of opportunity per quarter, per company, per node. Now, if we look at a TSMC customer, Apple, 5 nanometer wafers are getting quite expensive, so I calculate that the 15% die area reduction there would save them $18 million a month. And it's almost hard to calculate the value of putting non-volatile memory in the hands of chip designers at advanced nodes because that doesn't exist yet. Also, CeRAM allows you to program the resistance level. And this could unlock the holy grail of analog neuromorphic AI. If we're successful here, this would be a quantum leap for energy-constrained AI and systems exactly like NASA's. Additionally, in traditional memory, the same characteristic can be used to store multiple logical bits in the same physical bit. That's a trick that NAND uses to lower costs even more. So what I've described to you hits a lot of markets: commercial, government, IoT to data center, and it provides also a lot of this extreme environment at no additional overhead. So it could be a big leap in extreme harsh environment electronics as well. That's why it can address a lot of past and present focus areas highlighted by iTech. And it will probably open up markets that currently aren't serviced by microelectronics at all. So how do we translate this promise and advance our business plan? The bottom line is we're applying the successful ART business model, but in memory IP. And that business model has 2 big components: good IP capture and a good reference flow. For memory, the analogy to reference flow is sets of devices produced on arrays in relevant CMOS process flows. Now, we've done the IP capture. We're in this translational research phase. All of the components of this are well understood and defined in our industry, but they are by no means easy. They're also not quick, and they're not particularly affordable. So while I've shown you some key proofs in hardware for this translational research phase, we expect completing this phase will take us 2 years and will cost $20 million. So the problem for us on this government-focused path of ours is there's a well-acknowledged gap in funding of mid-TRL microelectronics. It's well understood. It's being addressed potentially by DARPA, the Congress, what have you. Cerfe Labs can't wait that long. And we would argue that NASA shouldn't either. So it's a particularly opportune time for us to be talking to the iTech community as we're discussing our funding planning going into next year. This includes, of course, additional grant funding. There are various state-level initiatives in microelectronics. There are strategic investors as well. And while our observation is that VCs typically don't align with the timelines of microelectronics R&D and ROI, and additionally, VC funds tend to direct to Asia and not towards low-volume government concerns, we're beginning some discussions there as well. So we feel strongly there's a synergy on this government focus with a logical engineering progression from lower volume to the commercial market, and we solicit your help in helping us continue along this way. And I'll remind NASA, you've invested in novel microelectronic materials before. This example, the material was silicon, and that turned out pretty good for everybody. So we are excited about the opportunity to talk to you today. We think it's a technology that fits the iTech mission and can advance NASA missions in the future. And I'd like to leave you with one other thought. While memory is the obvious opportunity here, when you have a new device, it's based on new materials, it's actually unlocking new kinds of physics. There's going to be opportunities in many different ways. So as we continue this path, we feel confident we're going to unlock optoelectronic opportunities, sensor opportunities, RF opportunities, many others. As we go along, that will help NASA missions in many different other ways. If you're interested in more about the technology, we have a primer on our website. Feel free to contact me as well. And thanks again to iTech, and thank you all for staying to the last talk.